Hello, everyone. Can you hear me?
Yes, we can hear you.
Thank you. I want us to start. Now, yesterday we began looking at algebraic structures, where we began by examining groups. Then after that, we shall be going to look at rings, fields, and other structures. So we defined groups. A group we defined, we say that it's an empty set together with some binary operation, that this binary operation be addition or multiplication. But in the meantime, we began by looking at a general binary operation, this circle, which meant either addition or subtraction, no, addition or multiplication. And that this binary operation must satisfy these four axioms. That is for the general group. Then we also looked at what we call a commutative group or abelian group. We say that an abelian group or commutative group, apart from this axiom, which we call a commutativity axiom, that a commutative group must satisfy. Now, so that was about the definition. After that, we began looking at examples of groups, and we saw that the set of integers is a group under addition. It's not a group under multiplication. It's a group under addition. This is a set of integers, and I told you what a set of integers mean. For instance, if we have the integers to be a set comprising of all the negative numbers, zero, and all the positive numbers. So this is a set of integers. We say that this set of integers, if you give it the operation addition, then this becomes a group. So we either write it this way to mean it's a group under addition, or we may want just to write it like this, and somebody will understand that you mean that it's a group under addition. So you're either writing it just as Z, or if you want to be very much specific, and then you'll add this binary operation, and both imply that is the set of integers is a group under addition. So it can never be a group under multiplication. So you can never write anything like this multiplication. You can never write something like that. It can never be a group under multiplication. Now, we said that we can also remove zero from a set and see whether it becomes a group. One that the groups that become, the sets that become groups when you remove zero from them. But the set of integers is not one of those sets. It's not one of those sets. So when I remove zero from it, it fails being a group. So it does not become a group under addition. And so it's never a group without a zero. So that is what and then we also say that if you have a set of integers and then multiplied by any number, the result that you get again will be a group. That result will again be a group. And then I showed you an example of the set of integer or even numbers. So this is a group under addition. This is a group under addition. So in fact, you can write it that way, or you may just want to write it like this, and it will mean the same thing. It's a group under addition. So what is this set? This is a set of even numbers. So you're just taking this set of integers and you're multiplying by 2. So where there is -8, you have -4, you have -8. Where there is -3, you have -6. Where there is -2, you have -4, and so on. So this goes up to 6 and so on. So it's a set of even numbers. So this, therefore, is a group and addition. It's a group and addition. So for you to tell whether something is a group and addition, we just emphasizing that you have to go through the axioms, the 4 axioms above, and see that they're all satisfied. If one of them is not satisfied, and then the set fails being a group, it does not become a group. So I'm just going through what we went through so that you get that understanding. So we looked at this set, and the question was, is this set together with addition a group? Is it a group? Together with additions operation, is it a group? And we said that the answer is that this is not a group, because we saw that it does not satisfy the closure property. It does not satisfy the closure property. For instance, when you look on the right side, the last number here is 5. So if I take 4 plus 5, for instance, I get 9, and 9 is not a member of this set. 9 is not a member of this set, and therefore we say that this set therefore fails being a group. So it's not a group and addition. So just once you give one property that makes it fail, that is enough. Then we also talked about set of rational numbers. We said that set of rational numbers with a 0, the way it is, with a 0, this is just a Q, with a 0 is a group and addition. Is a group and addition. When you remove 0 from it, and this is how you remove 0 from it, by putting a star. And so this then becomes a group under multiplication. So in fact, this reminds me when we were leaving, when I looked at the messages after the lecture, I discovered somebody had asked, how do we tell if it's with a 0 or without a 0? So for instance, I'm answering that question. For instance, if it's just written this way, then this one has a 0. But if it's written that with a star, then it means it's without a 0. So that is how you tell. So if it is with a 0, you consider it as for a group and addition. If it's without a 0, you consider for a group under multiplication. Because and you see, once you remove 0, you removed the identity element for addition. The additive identity element, you removed it. Now, so that is what is here. You remove 0 from it, becomes a group under multiplication. Now we looked at the matrices, and we said that matrices would also form groups, but they will not be commutative groups. They will not be commutative groups because if you have a matrix A and B, that product is not always the same as B times A. So commutativity is not satisfied. And then I gave an example of this set. The set comprises where A is that, B is this, C is that, and D is that. And the question was, does this set form a group under multiplication? So in fact, the other way of writing it, I'm just emphasizing, the other way of writing it is just like this. Does it form a group under multiplication? So this is multiplication. Or if you want, you can write it as this to mean the same thing. So the question is, does it form a group under multiplication? So to answer this question, we formed a table. And on this table, we are multiplying each of these elements, and we want to see whether the result is a member of the set. By multiplying those elements, we want to see if the result is a member of the set. And when we did multiply, this was our table. So we saw that when we multiplied A and B, we got B. A times C gave us C. B times B gave us A. B times C gave us D. B times D gave us, B times D gave us C, and B times D gave C gave us D, and so on. So what this tells us that you see, every time we're multiplying any two elements, we are getting another element of the set. So this tells us that the set is closed. Closure property is satisfied. And then by looking at these elements, we realized that multiplying A by n of the elements did not have any impact to the element. For instance, A times B just gave us B. A times C gave us C. A times D gave us D. This then says that A is the identity. A is the identity element. The element which has no impact on any other elements. So that is another property which has been satisfied. That this group has the identity element, and the identity element is A. Now, the other property that we look at is every element should have an inverse. So when you look at B, the inverse of B is B, because B times B is given as identity. So the inverse of B is B. The inverse of C is again C, because the product gives us the identity. The inverse of D is D, and the inverse of A is A. So every element has an inverse. So that property is satisfied. And associativity comes in, is now automatic, because this is a multiplication. Even if it were addition, again, it will have come in automatic. Once the other axioms are satisfied, associativity is always automatic, it comes in automatically. You don't need to stress yourself showing it. Now, I also gave another example. And so that table that we just looked at, we call it multiplication table, or we can call it the Cayley table. So in fact, today we want to see how to draw that table using Rust. And so that is what I'll be doing. We looked at this example also and the same explanation. Now, the set of residues modulo n. These are integers modulo n. I told you what residues are. If you're given mod n, then the residues are from 0, 1, 2, all the way up to n minus 1. These are what we call residues. So for instance, if we have z raised to 7, then this set has the residues 0, 1, 2, 3, 4, 5, and then 6. This is what we call that. So this is the group. This is the group, and these are the elements of the group. How many are they? 1, 2, 3, 4, 5, 6, 7. 7 elements. So this group has 7 elements. What about this one? This one has n elements, n. What about this? This one has 9 elements. Has 9 elements. The thing is, this one still has a 0. They still have a 0. So that is why you can see it is 0, 1, 2, 3, 4, and so on. Now, if you remove this 0, if the number here is prime, then it will be a group. Z star, you remove 0. If the number here is prime, so that means the elements are 1, 2, 3, 4, 5, and 6. So this will be a group. It will be a group. But if the number here is not even, for instance, this 8, and you just remove 0. If you just remove 0, it will not be a group. So for it to be a group, for this to be a group, if the number here is not prime, for this to be a group, then you need to have elements which are relatively prime to n, to this 8. Elements which are relatively prime to 8 and are less than 8. For instance, we are talking about 1, we're talking about 3, talking about 5 and 7. So this now is a group. This now becomes a group. So if it's Z star, the number here, if the number here is not prime, then the elements here should be relatively prime to this number for it to be a group. For it to be a group. Otherwise, it will not be a group. And that's what I've defined here. That's what I've defined here. I've said the set this is of residue of classes, so the GCD, where the GCD of A and N is 1, under multiplication forms an abelian group. So this fact is here. GCD should be 1. If the number N here is not relative, if the number here is not prime. Of course, even if it's prime, again, it's the same thing, that what is inside are numbers which are relatively prime. For instance, considering this 7, the numbers which are inside are relatively prime to 7. Now, so that in fact is part of what we need to know for us to create those tables in Rust. That's part of what we need to know. Creating a table, an addition table in Rust is very easy. Creating an addition table in Rust is very easy. What you only need to do, you will need to create this row, first of all, this row, the first row, the header, this header row. And after you've created that header row, for let me say the header row is 0, 1, 2, 3, 4. You will then create this column. You'll create this column. And then what you'll be doing, so this is the row, these are the rows, so the horizontal ones are the rows. So you'll be looking through the ith row, and then you look at the column. So you just look at the row and the column and you get the sum. So the sum is what you write. So this row and that column, you write the sum there. This row and that column, you write the sum. So this one, you're not the one writing, but the Rust has to know that that's what it's supposed to do. It is supposed to write the first column, then this the first row, and then these columns. Then after that, it will be adding the elements of the row and that of the column. So I times j, where I is the row and j is the column. So then, and again, then after that, it comes to the second row, and then this ith element adds this jth element and writes the result there. So that's what it will be doing. So creating these columns in Rust becomes very easy, especially the addition columns, the addition table. But now, for this multiplication table, you must first of all, the Rust must first of all know that the elements that it will be considering will be elements which are relatively prime to n. So in this case, for instance, this table, my n is 5. So what Rust would then do would first of all look for elements between 1 or between 0, not between 0, between 1 and n minus 1. And then check those which are relatively prime to 5, first of all. And so that means, in fact, that's not the first thing. The first thing is for it to know that they're relatively prime. Just a minute. Now, so the first thing that this Rust will be doing, First of all, before it comes to the issue of which ones are relatively prime, for it to tell if they're relatively prime, it's getting the GCD. It's getting the GCD, so the GCD of these values, A and N, it's finding if the GCD is 1, then this value is taken to be relatively prime. It's relatively prime to N. So supposing we have numbers from 1 to N minus 1. So what the Rust will be doing, first of all, it considers 1 and N, finds the GCD, and to see whether that GCD is 1. Then it proceeds to 2 and N, finds the GCD again, proceeds to 3 and N, finds the GCD, and this happens until N minus 1 with the N, and again the GCD. So those which have GCDs of 1, those are the ones which are relatively prime to N. So if you're writing Rust code to do this table under multiplication, then you have those two functions. One function is the extended Euclidean algorithm, or no, not just the Euclidean algorithm, the one that will be finding the GCD. So you need the Euclidean algorithm to find the GCD. And then after that, you also need a function that will be telling those which are relatively prime. Relatively prime. So Euclidean algorithm, you will just be finding the GCD. You'll find that one has the GCD of 1, another one a GCD of 2, another one a GCD of 3, and stops at that. Then this relatively prime function now comes to these GCDs and picks those which have GCD of 1. Picks those which have GCD of 1. So those are relatively prime. And so those are the ones which will then be here. Those are the ones which will form this row and this column. So then you have now a function to create a table. A function to create a table. So a function to create a table now picks these values, which are relatively prime, and then it must know that to get a value here, it requires the value in this row and a value in this column, the product of that, and then mod n. Mod n again takes this value, and then this value, this one, the value in this column, and the value in this row multiplies, then reduces mod n. Then 2 times 3, 6, mod 5 gives you 1. Then 2 times 8, mod 5 gives you 3. So that is what, so those are 3 functions, and then the main function. Those are 3 functions, and then the main function. But the addition table has only 2 functions. One of drawing, and then the other one of just the main function. So let me look at the addition table first of all. The Rust code. The Rust code that creates a function that generates and prints addition curly table for this, for Zn. Now, so as I've said, that what you need the function for addition table. And then you need the main function. Those 2 are enough. Now, so what does this addition table function do? First of all, I've defined it to be U64, and again, you can change. So it's only taking one value, n, and that is the mod. It's taking one value, and that is the mod. Yeah, the mod, if you want your mod to be 15, and your mod to be 5, so that is what this addition table function takes. Now, so it prints, this is the header, it prints the header. So the header will be addition table mod, if you wanted 15, it will read addition table mod 15, where your 15 is this n. So it will print the header. Then there's this print, and there's a bracket. So this is just, this bracket is just the space where it will be printing that header. That is where it will be printing the header. So you want to print mod 5. If you want, your n is 5. It will consider for I between 0 and 5. That's what it has said for. This is that's a loop. That's a loop for I, where I is between 0 and 5. 5 is our n in this case. So this part is telling the Rust code that this is our I. So what the Rust code is doing in this space of the first column, then the first row, in this space of the first row, this Rust this is the command to tell Rust code to print the I, to leave some space of 4 inch, around 4 inch, 4 inch or what, well, around 4, that is just a spacing of it's 4 inch, and then write I to the right of that, to the right of that space. So for instance, I have that some space of 4 inch, and then I write 0. Then some space of 4 inch, I write 1 on the right of that space. Then some space, and then write 2, and then some space, and then write 3, and then some space, and then write 4. So it's just, this is just a command that leaves some space. And then on the right of that space, write I. Write I. Now, after it has done this, this is the header, the first row. After it has done that, there's this command print. So this command is telling it to go to the next line. This command is just telling it to go to the next line. So it comes to the next line again. The next line, again, it writes the first I, which is 0. This case, which is 0. And then that is now want to begin printing the table. The next line, we're beginning to print the table. And then it's saying this print, just before it prints, it's telling from this space, from this one row to the other, from one row to the other, leave a space of 2 inch. Give a space of 2 inch. Then write I. Then write I. I is the row, that element in the row. So it will leave a space of 2 inch and then write I. And that again will happen for all I in the range of 0 to n. For all I. So again, it will move the next space, write I, then write I, then write I, just leaving a space of 2 inch, then write I, leaving a space of 2 inch. Then after that, there's something here. For every j in this range, for every j in this range, find the sum. Find the sum of I plus j. But there is a space of 4, first of all. Leave a space of 4 inch. Leave a space of 4 inch. After leaving that space, find the sum of I is the row and j is the column. The result, divide by n and write the remainder. The result, divide by n and write the remainder. For instance, in this case, 0 plus this 0. This one I was supposed to have written it somewhere here. So 0 plus this 0, the answer that you get divided by n, in our case, is 5. And then write the remainder. Then 0 plus this 1, the answer that you get divided by n and write the remainder, and so on. You come up to this point, 4 plus this 4, the answer that you get is 8, divided by 5 and write the remainder. After you've done that, there's a print here, print. This print is telling you to go to the next line. That's what print says. So it does for one line, then there's a print, go to the next line. It does that line, that row, up to the end. Then this command print tells it go to the next line. Then it does that again. This command print tells it go to the next line. And so that process continues for all j in this range, for all j in that range. Okay, let me just show you the code so that we look at it. Are you able to see it? Are you able to see the code? Cecilia, can you hear me? People cannot hear me. Hilda?
Hello, I can hear you and I can see it.
Okay. Let us run it. So at the bottom, can you see something at the bottom? Hilda?
Yes.
What are you seeing? What am I highlighting here?
Going down, that's the Kaylee table for the unit.
Oh, the one I've highlighted. The one
Additional
I've highlighted.
table, mod 15.
Yes,
Addition
yes.
table, mod 15. Yeah.
Yes, that's mod 15. It's bigger. It has gone beyond that. Let me reduce the mod a bit. Reduce the mod to 5. And then run this. Reduce to mod 5 and run. So mod 5 is smaller, so it does run. So what I was saying is it commands this to leave some space of 4 inch for every, between one column to the other, but between one row to the other, just 2 inch to a space of 2. Then from one row to the, from one column to the other, a space of 4, a space of 4, a space of 4, and so you write that I after that space. That is what I'm reading, what I'm seeing, that is what is here. I'm highlighting in the code. Print 4 inch, then I to the right of that. I to the right of that. And then after that, there's this print command, which just tells it, go to the next line. So the next line, now we begin writing the table. And again, begin with a loop for I between 0 and n. So that this means just 0 up to n minus 1. 0 up to n minus 1. A print, and this is 2-inch. So we are beginning a next row. So 2-inch and then I to the right. So that'll be 2-inch. So this is the next line. 2-inch from above. Then I. Okay, so you'll do the column first of all. You'll do the column first of all. All the column, this column up to here. Then after that, you come every row, complete it as you get the sum. And the sum is here. This is where you're getting the sum. So complete the row now. Take the I plus the J, where I is the row and J is the column. So for instance, in this case, you're taking these 2 and these 2, you're summing up and you're writing the answer here. That's what it's saying at this point. So just look at the column, the code just 1 minute, and then I'm coming back. Yeah, so that is how we do it. And you've noticed that for you to do this again, you need to have understood the modular arithmetic, because that is what we are applying at this point. It's I plus J mod N. So that means the remainder. That's the remainder. So let me again explain how that code works. Then we look at the multiplicative table. So this is the explanation. There is an addition table function, and that function takes us, we've already said it takes a single value n, where n is the modulus. And then under this function, we have the printing the header, the point where you print the header, and it says addition table mod n. That is where print, it says print addition table mod n. That is where we are printing the header. Let me just show you that. This is what I'm referring to. This is what I'm referring to. Printing addition table mod n. So this is where we are printing the table. So this prints the heading, indicating that the modulus used for addition. It prints the heading and then indicates the modulus that was used. So the modulus is n. Then there is this point where I said print with a bracket, this bracket. So this prints the initial space for formatting the header. Just prints the initial space for formatting the header row. The header row is the first row. the first row of 0, 1, 2, 3, up to 4. That is the header row. So that is, it prints this. So that is why we'll be formatting the header row. Then after that, there's a loop that says for I in 0 to n. So that means that we'll consider every I. We'll consider 0, consider 1, consider 2, consider 3 up to n minus 1, and then print those columns. Not necessarily, but those first elements, the first row, 0, 1, 2, 3, and so on. So we're doing all of them up to n minus 1. Then after that, print, there's this print. So this prints each number right aligned in the field, then leaving a width of 4. Just leaves a width of 4. So there's a 4. And then for a space of 4, then you write I or 0, a space of 4, then write 1, a space of 4, then write that, and so on. So that is what that says. Then from there, we have print table. You have print table. This part is the part I'm referring to as print table. Now, so this, what it will do, it will print the rows. It will print the table row. So for instance, we had already printed the header. So it then comes, then just writes the initial points in the row, the initial points in the row, or it can even, I think it can even write the entire row, can even write those rows. For instance, we have 1, 2, 3, can even still write 1, 2, 3, 1, 2, 3. But then what it will be doing at this point, it will be not necessarily. It prints 1, 2, 3, then just prints the initial ones here. This side prints 1, 2, 3. So then it will now come this and that and write the result. Come this and that, write the result, this and that, and write the result, and so on. But now it does for the entire row. It does for the entire row. Then after that, there's print to command it to go to the next row. So that's what I've said. What I've said here, that print this space, there's this space. So this prints the row header. That is the current row. The current row, for instance, if it's talking about row 1, it prints row 1, but there is an I coming after the space. There's an I coming after the width of 2. And then after that, there's this summation. There's this summation mod n. So it calculates that summation, then does mod n. And then after that, that summation should come after a space of 4 width of 4. Then there's this print. This print is what I said, it moves the next line after printing each row. So after printing row 1, there is this print in that tells it to go to the next line. Then after printing row 2, there is this command again telling it go to print to row 3, and the same process continues. At row 3 again, considers this value plus the values above and gets the summations. Gets the summations mod n. So after it's done with that, there is this command telling it to go to the next row. So the next row again considers the value here on the left side and the values above, adds and puts the results mod n. and so on. So this process continues until we've reached n minus 1, until we are at n minus 1. So the main function, this is where we're just inputting the value n. And then what the main function does, it calls the addition table function. And the addition table function does what you've just explained. So you can see the main function, this is the main function. You input your n, and after inputting your n, it calls the addition table function. It calls on that addition table function, and the addition table function is here. It does what we've just explained. And so after the addition table function has done that, the main function now again would print those results. Now, so what about this other table for multiplication? For multiplication, I'd already explained and said we have functions. The first function is the one which is calculating the GCD, and then the relatively prime function. And then after that, we have the function for drawing the table, just like the one we've explained above. And then from there, we have the main function. So the main function, this is where you input your value, n. So once you input your value n, the main function calls on the relatively prime elements function. It calls on this. And again, it also calls on the multiplication table function. So it calls on two functions. The first function it calls is the relatively prime elements function. And then it calls on the multiplication table function. So after calling on the relatively prime function, the relatively element function realizes it's supposed to arrange the relatively prime elements, but it does not have them. So since it does not have them, it also calls on another function. So this is the relatively prime element function. It realizes it cannot do that, so it has to call on the GCD. On the GCD function, just a minute. Yes. And so that the GCD function, first of all, does the GCD. After doing the GCD, then this will pick. So that is why it, you see, it has called on that. There's this GCD. It requires the GCD of I and n, and it cannot do that. It cannot do that. So this one has to do that first of all. So this one does the GCDs, all the GCDs for between 0 and n. So a and n, let me say 1, 2 and n, 3 and n, 4 and n, all the way up to n minus 1 and n. So it does all those GCDs, all those GCDs. Now this one will just be picking from those GCDs. It will just be picking. So that relatively prime will just be picking those which are relatively prime, those which have GCDs of 1. Those which have GCDs of 1 is the one it will be picking. And then it picks and stores them here. Stores them here. So stores the numbers which have GCD of 1 in this new vector, empty vector. So there's a mute here. The mute here means this vector is changing. So let me say for the first time, it picked 1. So that vector would have 1. Then when the GCD of 2 and n is done, it happens that 2 also has a GCD of 1. So this vector changes now. That is why we talk of mutable. So it changes to 1, then 2. It has now 2 elements, which are relatively prime to n. Let me say 3 is done and 3 is not relatively prime, so it's not picked. 4 is done and is not relatively prime, it's not picked. N minus 1 is done and then it's relatively prime. So this again vector changes. So this vector has 1, 2, it now has 1 n minus 1. That's why it says mutable. So we push this push the result. Push the result into the vector. So that is what it's doing. So once it discovers that 1 is a relatively prime, that 1 is pushed into that vector space. And then when 2 becomes a relatively prime, 2 is also pushed. So that's why I say result push. So that the final result here at this point will be that of relatively prime numbers. Now, earlier on, I had explained how we get GCD using a greatest common divisor and this Euclidean algorithm. I had already explained that, and we had already had the code for this. But I'll just repeat how to get the GCD. How to get the GCD of two numbers. So we begin with the two numbers N and B. Want to find the GCD of that. So how do we begin? We begin by letting X be A. Letting X be A and letting Y be B. Remember, we want to get the GCD and write it in the form of AX plus BY is equals to GCD. That is what this function is doing. It wants to find the GCD and write it in this form. But what we're interested in is that GCD is what we're interested in. So what it does, let X be A, let Y be B, and then while Y is not equal to 0, this is what this means. While Y is not equal to 0, perform what is inside here. While Y is not equal to 0, that is what this means. This is a loop. So it's just telling the function, the Rust code, that while this Y is not equal to 0, perform what is inside here. So that means whatever is inside here will be performed until Y becomes 0. So when Y is 0, they exit the loop. And whatever X will be the GCD. Whatever X will be at that point, because they're all mutable. They're all changing. X is changing, Y is changing. So for instance, if we had something like 10 and something like 7, and want to find the GCD, so in this case, our A is 10, our A is 10, and our B is 7. So we then say, let X be A, and let Y be B. And then while Y is not equal to 0, so in this case, our Y is 7. So while Y is not equal to 7, is not equal to 0, perform what is here. The first thing that is inside here, let this Y be temporary. Let this Y be temporary. Let Y be temporary, so temporary. So the Y is just temporary, 7 is temporary. So once it is temporary, what is the Y? What is now the new Y? Because this is the original Y. It has to change, keep on changing. So what is Y now? Our Y now becomes X divided by Y, the remainder. So X is 10 divided by Y, the remainder is 3. What about X? X becomes the temporary, the value which was temporary here. The value which was temporary was 7. X becomes 7. So this process continues until Y becomes 0. So you can see we've done the first part and Y is not yet 0. So since Y is not yet 0, again, we repeat the whole process. We say let temp be Y. Let temp be Y. let temp be y. Now, so what is our y now? Our y now becomes x divided by y, the remainder. Our x is 7, and y is that x, y goes into x twice, and the remainder is 1. So that is now our y. That is now y. What about our x? Our x is the temporal value. The temporal value, that's what it's saying. X becomes the temporal value. The temporal value is 3. So y is not 0. Y is not 0. So again, we repeat the process. We say let temp be y. Let temp be y. And so what is our y now? Our y becomes, and the formula is here, the formula says x divided by y, write the remainder. X divided by y. So when you divide 3 by 1, the remainder is 0. So what is x now? X is what was temporal. So y is 0. The thing was, while y is not equal to 0, perform what is here. So once y becomes 0, exit. And when you exit, the GCD becomes x. That is what it's saying here. When you exit, the GCD becomes x. So we have exited. So the GCD therefore is 1. For 7 and 10, the GCD is 1. So this is what this function is doing. So this function will do that for 7. Supposing our n is 10, it will do for 7, it will do for 6, it will do for 5, it will do for 4, and so on. It began with 1. It begins with do with the 1, do with the 2, do with 3, and so on. So that is 1, 2, all the way up to 9. So it's doing this. This is the process that this function here is doing. So I've just showed you how it will do in the case of 7 to show that the GCD between 10 and 7 is 1. That's what it will do. So again, it will follow the same process to do the GCD of 6 and 10 and show that it's 2. And then the GCD of 5 and 10, it will be 5. And then it will be storing those GCDs. Then this one will be picking. This one will be picking from here. So once this one does the GCD, so this one is just waiting. If it does for 1 and 10 and finds that the GCD between 1 and 10 is 1, this one pushes. So this was 1 and 10, 1 and 10. So it says if GCD of I and n is 1, push that I into this vector space. Push the result into the vector space above. So this one does 1 and 10. It finds the GCD is 1. So this one comes. For this I between that, it has found that the GCD of 1 and n and 10 is 1. So it pushes 1 into that vector space. Then it waits. This one does 2 and 10. The GCD is 2. So there's nothing to push. And then it does 3 and 10 GCD. It finds the GCD is 1. So again, it pushes. So now we have 2 values. So that process continues until they have considered all the values between 0 and 10. 9 minus and to 9. So that's what this function will be doing. So that is how the GCD function will be working. And of course, if you can still remember how we did this and we explained that, of course, I've done the same, how the GCD is calculated there and what this other relatively prime function is doing. So this one is just waiting for the function above to perform the GCD. And once the GCD is 1, it pushes that result into the vector space. And if the GCD is not 1, it does not push anything there. It waits for the next I. And so once they have done all that, once these two have done all that, and once this one has stored all the numbers which are relatively prime to n, now it comes to the multiplication table function. So the multiplication table function does what we've already explained for the addition table. It prints the header, print multiplication table mod 10, and then it creates a space for the first row, creates a space for the first row. Then after creating the space for the first row, it comes and prints that first row, but leaving some width of 4 and printing a value after that. And then there's this print telling it go to the next line. So at the next line, it's leaving again a space of 2 to come to that next line. Leaving a space of 2, and then it comes to that next line. And then at that point, it writes the values after some space, writing A after some space. Then after that, it has this row, which has 1, 2, for example, and then it has this other row, a column, with, let me say, 1, 2, 3. So these are the numbers which are relatively prime. And then it's told, take the I value, the value of A and the value of B, multiply the result, and divide by the mod, write the remainder. That's what this is saying. But after some space, give it a space of 4, width of 4. So it gives us a space of width of 4, then multiplies this. Supposing the mod was 5, so this times that will be 1 divided by 1. This times that will be 2 divided by 5, the remainder will be 2. It does the whole thing here. So this will be 3, this will be 4. Then there's this command, print, telling it to go to the next line. Comes this next line, again does the same thing. 2 times that will be 2. 2 times that will be 4, divided by 5, the remainder is 4. 2 times that will be 6, divided by 5, the remainder is 1. 2 times this will be 8, divided by 5, the remainder is 3. So that's what this value is saying, that multiply 2 times 4. The answer that you get, divided by the mod, which is 5, and write the remainder. That's what it does. So once that is done, once it does for all those, the result is printed. So that code, again, I've explained it here, but let me just show you how it runs, and then you can look what are the explanations. Now, so I hope you can see it. I want mod. Let me take a smaller mod because of this space. Let me do it mod 7. So let me do it mod 8 first of all. It has to first of all calculate values that are relatively prime to 8. So first of all, finds the GCD. Finds the GCD here. Finds the GCD. And then after finding the GCDs, this function will pick only those numbers which had a GCD of 1. Those which are relatively prime, it will pick only those. So this one will now be using those values which have been picked, those which are relatively prime, to draw the table. This function will be picking only those and drawing the table using those. So that's what we want to see. We want to see that it uses only those which are relatively prime to 8, and gives us a table. So it has found that mod 8, multiplication table mod 8, values which are relatively prime to 8 are 1, 3, 5, and 7. So it puts them on the column, the row, and then again column. Here, the first column, then begins multiplying. So you put according to what you want. If you want a bigger value, you want mod 16, again, you can still do that. And it will do that. It will do that. That's a table now for mod 16. It has put the values which are relatively prime to 16. And these are the values. So you can see, if you multiply 5 by 3 is 15. If you multiply 5 by 5, will be 25. 25 divided by 16, the remainder is 9. So that is what you see here. 5 times 7 will be 35. 35 divided by 16, the remainder will be 3. So that is what it does. So how the code works is here. I've explained how we find the GCD. You look at that. And of course, you have the other video, which talks about the Euclidean algorithm, which explains how Euclidean algorithm does the GCD. Then we have the relatively prime elements function, and its function is just to find integers from 1 to n minus 1 that are relatively prime to n. And so I'll say that it creates an empty vector. So it creates an empty vector to store relatively prime elements. So this empty vector here is just to store relatively prime elements. So once it gets one which is relatively prime, it checks. If it gets one which is relatively prime, it pushes that to that empty vector. Pushes that to the empty vector. And again, if another one comes, it pushes it there. And that process continues until the whole thing is done. After that, we have this multiplication table function. And this one is now using the values which are relatively prime from above to create the table. Then, yeah, that is it. Then we have the main function. And its role is just to finally print. It had called on the relatively prime elements function. Then it had called on the multiplication table function. Then once those ones have done what is required, the values are then, the table is then printed. Thank you. I want to end there unless there's a question. Okay, if there's no question, I think, is there an announcement? Alex? So I think let's end there. We meet next, we meet on Monday.